Hello and welcome to this week's video for MMI701 multimedia signal processing. In this video we are going to talk about discrete time signals and systems. So before we even start, we should perhaps define what a signal is. It's a series of numbers in time and or space which quantify a property. So for instance, sound pressure might be one example when you measure it. Temperature might be another. Electrical muscle activity, light intensity. In fact, pretty much anything, any quantity that you can measure constitutes a signal. So let's define different types of signals by way of their different properties, their dimensionality, how many variables it includes, whether it's temporal or spatial, whether it's continuous valued, whether it's continuous time, etc. So let's assume that we have a thermometer where we're measuring the temperature at a given position, x0, in space. So we're talking about a single position, x0 in space, and let's say we have a thermometer which can provide us with continuous valued readings. So let's say it's a mercury thermometer and we're able to measure with infinite precision on the scale it provides. So then we have a unidimensional signal because we have a single value which changes in time, which is also univariate. We're measuring at a single point, so it's unidimensional. We have a single value, then it means it's univariate. We're measuring in time, that means it's a temporal signal. It is continuous valued. For every time instance, we have a value which is continuous. And it's continuous time, which means we have a value at every time instant. Now, if we have an infinite number of thermometers, or if we have the ability to measure the temperature at all points within that room, so that is all points x within that room, and let's say we're measuring it just once, we're taking a snapshot, and that snapshot is taken at t0, then we have a multidimensional signal, which is still univariate because the signal has a single variable, which is temperature. Our signal is spatial. It is continuous values still because our infinite number of thermometers all have this, mercury thermometer which can measure temperature with infinite precision. And it's continuous space because we're measuring at every point inside the room. So these are kind of hypothetical signals because it's not easy to acquire such a signal, right? Then if we measure temperature at all points within the room at all times, we have a multidimensional signal because we are measuring at every point. It's still univariate because it's still temperature only. It is now spatiotemporal because we're measuring in space, but we're measuring a temporal signal. It is continuous valued still. Our ideal thermometer can give us infinite precision readings. And it's continuous time, so we can measure at all times. Now, how about a multivariate signal? Well, the thermometer example doesn't work so well in this case, but we can think about, say, a vectorial quantity, say, particle velocity, which has three components, x, y, and z components. Then we have a multidimensional signal. And if you're measuring our multidimensional signal, our particle velocity signal, at each point in space and at all times, then we have a spatiotemporal signal which is continuous valued, continuous time, and it's multidimensional and multivariate. By the way, in this course I'm going to use bold-faced letters, bold-faced math, for vectors. So when you see a bold-faced letter, it means it's a vector or a matrix. Okay, so finally, another example for a discrete valued and discrete time signal. Let's say you're going and checking how many people there are in a room, and you're checking that every minute. So you go in, check it, go out, then you go check in, then you go out. It is a unidimensional signal because you're measuring the signal at a single room. It is univariate because it's the number of people in a room. It is discrete valued because you cannot have half a person. And it's discrete time because you don't have any idea whether between the two measurements that you take with that room, the number has changed. So these are different types of signals. You know, you can just make this list bigger if you like. But, you know, these are just some examples. Now, in this course, we're going to specifically deal with temporal signals. We're going to deal with univariate signals, and we're going to deal with unidimensional signals. But in many things that you're going to do later throughout this program, this master's program, you're going to be dealing with multidimensional signals, in some cases spatiotemporal signals, etc. So, but in many cases you'll be dealing with discrete valued and discrete time signals. Now let's give an example about a continuous time sinusoidal signal. So our continuous time sinusoidal signal is given here, x sub a t. A stands for analog. That means we're dealing with a continuous time signal, continuous time, continuous valued signal. We have a sine omega t, big omega, capital omega t plus phi, where t can take any value between minus infinity to infinity. Now let's define these different quantities then. Say the first quantity that we would need to define is omega, capital omega. It is equal to 2 pi f, where f is the frequency. This is called the radial frequency. Okay, so far so good. And we have to define f as the frequency. That is, how many oscillations does the signal make in 1 second? The unit is hertz. And the unit for omega is radians per second. Okay, A is the amplitude. It is unitless. And let's also define the period, Tp, which is 1 over f. This is the period. Yep, period of our signal, and the unit is seconds again. Now these are all different parameters which define our continuous time sinusoidal signal. So what is period? The period is the time interval at which our signal returns back to its starting point. That means for period again, so let me write this in a different color, perhaps. Yep. So that means x analog of t equals to x analog of t plus k tp, and k could be any integer. So any integer. Okay, so far so good. So this is our continuous time sinusoidal signal, which is pretty simple. Our next example is slightly more complex. It is a continuous time complex exponential signal. Now, we are using J in here. For those of you who don't know what J is the imaginary unit. Now, I would assume that people from electrical and electronic engineering, graduates of electrical and electronic engineering, would most definitely know what J is, but for the sake of completeness, let me just write it down. J is square root of -1, so it's the imaginary unit. Okay, that's good. Now, this is a special signal which has this form. Xa of t equals to A, which is again our amplitude, times cosine omega t plus phi plus j sine omega t plus phi. Now you can see that our signal has both a real part and an imaginary part. And the magnitude of the complex exponential, this second part, is unity because it's cosine squared plus sine squared, which is 1. And the different parts of our signal are orthogonal to each other. That is, we have cosine and sine in the two parts, real and imaginary parts of our signal. Now, we're going to come back to this signal, complex exponential signal, as it's a very important signal. We're going to form our bases, which we use in Fourier transform, different flavors of Fourier transform using the complex exponential signal. And we're going to start with the continuous time complex exponential signal, which is very important. So we're not done yet with continuous time complex exponential signal. Now, another example is discrete time sinusoidal signal. Now, this is slightly different from our first example, continuous time sinusoidal signal, in that we have a signal which has an index n. So our signal has an index n which stands instead of time. Now, x of n is a series of numbers, and each number, each sample, represents the value of a signal at that given time instant. But the time instant we're talking about is not continuous anymore. So this signal does not have a value between n and n plus 1. It only has values at n and n plus 1, but it doesn't have a value at n plus 0.5. That is, n has to be an integer. Now, our definitions for the terms in here are slightly different than for our continuous time sinusoidal signal. For the discrete time sinusoidal signal, we have lowercase omega, which is again 2 pi, but this time lowercase f. This is still called radial frequency. But its unit is radians per second. Okay. Then we have phi, which is phase in radians, just as in the continuous time sinusoidal signal. It is the same. Then amplitude A is the same as well. A is the amplitude. It's unitless. and we have TP. I'm sorry. We have F, which is frequency. Which is number of oscillations per sample. Now, I need to make it absolutely clear that this is different than our original definition of frequency, which was number of oscillations per second. Now we're talking about number of oscillations per sample. So let me just write the unit, 1 over sample. So this is the definition for frequency in discrete time. And again, please do remember that the time index n is an integer. So it's important to know. So how about periodicity of our discrete time sinusoidal signal? Now, as in the continuous time sinusoidal signal, we are looking at cases, we are looking at lags for which the original signal has a value which is the same as the shifted version of the signal. So we're looking at a case where for a given frequency f0, or given radial frequency 2 pi f0, we have this relation, a sine 2 pi f0 n plus the phase offset is equal to a sine 2 pi f0 n plus big N, capital N, plus theta. So this is only going to work if 2 pi f0 n is 2 pi k. Now here we define n as our fundamental period, period, and we have 2 pi f0 n equals to 2 pi k, which defines the periodicity relation, which results in an important result for discrete time signals, discrete time periodic signals, that f0 is equal to k over n, where k is an integer. So let me just write it here as well. So k is an integer. That means the frequency of our signal is always a rational number. So this is a rational number. So let me just write it here. So that's a very important property of periodic signals that are discrete time. Okay, so how do we obtain then discrete time and discrete valued signals? Say for instance you have a sound card and you're speaking and you're recording your voice by a microphone. So what do you need to do? That's our question. So first of all, your speech is an analog signal to start with. And you need a transducer, in this case a microphone. That is a sensor which responds to pressure changes. More detail is not needed at this point, so if you're interested, there are courses like Communication Acoustics where we talk about microphones in much detail, but in this case, the signal that the microphone captures is an analog signal, which means we have an analog signal to start with. So here we have an analog signal x. Yeah, let's call this x of t. Let's drop the letter a for that. And let me just write denote that it's an analog signal. Now, there is a stage where we call sampling. Now, right now, we're not going to go into too much detail about sampling, but on week 7, we're going to talk about the sampling theorem. We're going to talk about it in detail, so let's keep it as such. And after sampling, we have x of n, that is a series of numbers which represent our signal in discrete time. So let me just write the property of that signal. It's a discrete time signal. Okay, that's all good. So we have a sequence of numbers which have infinite precision, but that's not good enough because we would still have to represent those samples on a physical device which can only accept a finite number of numbers. So we need to assign each of these samples, each of these values within our signal to one value within a set of values, and that stage is called quantization. And after quantization, we end up with xq of n, which is the quantized signal. So let me just write it underneath as quantized. But we're still not there yet, so we have to represent this signal, the sequence of numbers, in a way that is appropriate for the physical device that we're gonna process it, that we're gonna use it, etc. So after that we have the coding stage where we end up with basically bits. So 0, 1, 1, 0, etc. Okay, so bits. So then after coding we have a digital signal. And only after that we have a digital signal. But luckily enough, it is in many cases possible to base our understanding of signal processing prior to the coding stage. By the way, one thing that you should remember, here we're not talking about coding in the sense that we will be talking about compression. So this is something different. We're just converting quantized values to bits basically by coding. So it's not compression, it's a completely different thing. Okay, so these are different stages where we obtain our digital signal. Let's have a look at these stages in a little bit more detail. So sampling. So what is sampling? It is the process of obtaining a new value every t seconds. Say, for instance, you may be recording temperature outside daily at the same point. That means you have 60 times 24 as your t, so it's 80,000 something. Now, what we do then? We have an analog signal. That is your speech, that is the temperature, etc. And we look at it every t seconds, and we record its value at those instances. So we have x analog, that's our signal, and we're looking at that signal at nt, and we're mapping those values to our discrete time signal, which is x of n. So that is called sampling. So what are these different things then? So first of all, let's write t, let's define t as our sampling period. Okay, in seconds. And we also have to define something which is more commonly used than sampling period, that is the sampling frequency or sampling rate. Now remember, the process of looking at your signal every t seconds is a periodic process. That is why it's called the sampling frequency. We're looking at our signal, our analog signal, every t seconds. That means we are basically using a sampling rate which is, or a sampling frequency which is 1 over t. Okay, so it's also called sampling rate or sampling frequency. So then what we're doing is obtaining samples. Okay, so we are obtaining samples. Okay, we are obtaining samples at t equals to, well, t0 equals to 0, t1 equals to t, t2 equals to 2t, etc. And t sub n equals to nt. So this is how samples are obtained. Now, we'll see more on this later. Again, in week 7, we're going to go into more details. But for now, I think that is more or less what you should know about sampling. But let's have a look at an example. We have an analog signal which is a cosine 2 pi ft, so that's an analog signal which has a frequency of f, as you may remember, and a phase offset of theta. And we want to sample it. So let's sample it then. So what is, let me just write it here. So x of n is equal to xa of nt, which is equal to a cosine 2 pi f nt plus theta, right? Nothing else changes. We just substitute nt for lowercase t, that is our time variable. Now, we know that t is equal to 1 over fs, right? So let's just write it that way then. Because t is our sampling period, we can write it as 1 over fs, where fs is our sampling frequency. So a cosine 2 pi f over fs n plus theta. Now, we will define, so this is our sampled signal, we will define f, lowercase f, as f over fs, so the ratio of our frequency to our sampling frequency, and we're going to call that normalized frequency. Okay, so the reason why it's called normalized frequency is, as we shall see, the value is between minus 1 over 2 and 1 over 2 in the fundamental interval, or between 0 and 1. for property sampled LE3 signals. Okay, let me just make this a little bigger. Yeah, that's good. So let's have a look at how we sample a signal. So let's say we have this rather arbitrary signal, which looks like this. And let's say that we are sampling that at, well, doesn't matter too much, but let's say our sampling period is 0.05 seconds. So that means we're going to have one sample at each of these points. Right? So these are our samples. What does this mean? When we have, okay, so let me just write t here, 2t here, 3t, etc. Okay, where t is equal to 0.05 seconds. Doesn't matter too much, this is just a toy example anyway. But what happens then is, after sampling, we would still have a continuous time signal, sorry, continuous valued signal before quantization. And that would be something, if we want to obtain back our signal, that would look like something like this. Etc. Okay, so that will be our signal then. Now, let me just write some little details here as well, just to make sure that we're on the same page. So this is our time axis. This signal is x of t, and the red signal is x of n, our sample signal, and these points are the points at which we are sampling our signal, t, 2t, 3t, etc. Now, some important properties about how the frequency of our analog signal maps to the frequency of our the frequency of our discrete time signal, the normalized frequency. So let's just write these relations here. Yeah, for the analog signal, we have -1/2t is less than or equal to f is less than or equal to 1/2t. And yeah, remember that omega, or capital omega, the radial frequency is 2 pi f, which means that value is between -pi/t omega and, just write it a little bit clearer, omega less than or equal to pi/t. So this is the frequency interval for the analog signal. Analog signal. Now this is going to be mapped to frequency ranges for the discrete time signal. So let's put an arrow here, and we have -1/2 less than or equal to normalized frequency less than or equal to 1/2. So the fundamental interval is between -1/2 and 1/2. And for omega, that same range is between -pi and, so let me just write it a little bit more properly, -pi, the radial frequency is between -pi and pi. And this is the fundamental interval. Fundamental interval. Okay. So we will talk about sampling theorem more and in much more detail later. But I would like to state the sampling theorem at this stage because it's central to anything we do with signals, anything that we do with signal processing. Okay, so it goes on like this. If the highest frequency in an analog signal, x sub a of t, is b, that is the maximum frequency contained in xa of t, this signal can be exactly reconstructed from its samples when the sampling frequency is greater than 2b, that is twice the maximum frequency contained within the analog signal. And it's important to, well, it's in bold, but I would like to underline this. So you can reconstruct any sampled signal, right? However, if you want to exactly reconstruct your signal, then you need to sample your signal at least at twice the highest frequency contained in your signal. Now, for example, for human speech, the maximum frequency contained in the signal that you can record is about 8 kilohertz. That means if you sample speech at 16 kilohertz, then you're more or less fine. For music, that's a completely different story. You may have other signals which are not acoustic, then you may have different maximum frequencies, different sampling rates that you would need to sample your signal at. Now, twice the highest frequency in your signal is then called the Nyquist rate. Now, we're going to talk more on the sampling theorem. We're going to prove the sampling theorem on week 7. I'm quite excitedly waiting for it because the proof is so beautiful. I always take a lot of enjoyment from out of just showing you the proof. But, two things that you should keep on your mind about this. One is exact reconstruction, what sampling theorem says about exact reconstruction, and the other thing is the term Nyquist rate, which is twice the maximum frequency contained in the analog signal. Okay, so much for sampling theorem, and our next topic is quantization. So it's the process of assigning discrete values to a continuously valued signal. So you have a continuously valued signal, and you're trying to map that to one number from a set of numbers that you define. So quantization can be expressed as an operator operating typically on the discrete time signal, x of n, and you can have two different versions of quantization by truncation or quantization by rounding. So what do we mean then? Quantization by rounding, quantization by truncation. So let's say that we have a sample at n, so this is our sample, and this is, let's call this n0, and this is our sample x of n0. It's a continuous valued signal, and we would like to map it to one of these values. Okay, so let me just save it first, and yeah, okay. So one of these values, and these values are m plus 1 delta and m delta. Here, okay, delta is our quantization step size. Okay. And if we are rounding, if we're quantizing by rounding, we will be mapping our signal to a value which is closest to it. So we would be matching, we would be mapping that sample to this value. So this is quantization by rounding. And if we want to carry out quantization by truncation, then we get rid of the fractional part and we map our signal to this value, m delta. So that is quantization by truncation. So I just want to write the axis name here as well as n in samples, yes. Okay, so we said delta is our quantization step size. Now, if you're assigning a value between, well, from a set of numbers that are 0 to 10 to your number, to your continuous valued sample, then your quantization step size is 1, right? The difference between the two consecutive values in the set of numbers that you have. So that is your quantization step size then. Well, obviously we're not going to use that kind of quantization because that's not the point. But still, it is important to remember this. I mean, you can have any type of quantization. But in all cases, you can have, as long as you're using uniform quantization, you're going to have a quantization step size. Now, one thing that you should observe is that quantization results in an error, which is called quantization error. So let's write it down here as E sub q n, that is quantization error. So E sub q n is equal to the actual value of our continuous valued signal. I'm sorry, we're going to define it the other way. The quantized signal minus the actual value of our signal. Doesn't matter which way. I mean, we're going to deal with the energy of this signal. But anyway. So this is the quantization error. Now let's define our quantization step size once again. Okay, so we're going to have something slightly different here. So let's say that our signal varies between x min and x max. So let's say our signal varies between x min and x max. And we are using L equispaced numbers to represent it. L equispaced numbers to represent it. Then our quantization step size is delta equals to x max minus x min over L minus 1. That's the number of intervals between the maximum number that you have in your set and the minimum number. Because you have L numbers, you're going to have L minus 1 intervals. So you're dividing that range into L minus 1 intervals. And this part, x max minus x min, is called the dynamic range of the signal. Okay, so x max minus x min is called the so dynamic range of our signal. So this is the definition for quantization error and the quantization step size defined with respect to the dynamic range of the signal. So there is this question then. What are the limits of quantization error for rounding? Now, truncation is a slightly different matter, but let's have a look at what errors we induce by quantizing our sample by rounding. So I'm hoping that you started to think about how these things work, but let's have a look at this. So let's say we have our quantized signal xq of n equals to m delta if x of n is less than m plus 1 over 2 delta. That is, our sample is below the midline between m delta and m plus 1 delta. We assign it to m delta because we are rounding, and m plus 1 delta if x of n is greater than or equal to the midpoint between those two values, m plus 1 over 2 delta. So this is quantization by rounding for you. Then looking at this, what would be the maximum error for quantization? Well, quantization by rounding. The maximum error will be bounded between minus delta over 2 and delta over 2. That is, imagine you're rounding and your sample is exactly at the midpoint. It's exactly m plus 1 over 2 delta, or exactly below or above it. That means the maximum quantization error that you're going to have is delta over 2, which again means that your quantization error is bounded between minus delta over 2 and delta over 2. So this is the bound for quantization error. So that's something important, and we're going to talk about how we deal with quantization error in the next couple of slides. Okay, so this is a slightly larger template for us to work on, let's say we're sampling, we're quantizing a sinusoidal signal, and we have a zero order hold. That means we quantize and hold that value there. Okay, so that is how this works. So we don't have any linear interpolation or anything like that. That's the simplest quantization possible. So let's define this green signal as x of t. So I'm gonna try to find a more matching color for that. Probably not necessary, but anyway. So this is x of t. Okay, just let me use black because it's not gonna look so good anyway. So this is x of t, and we are looking at this little box here. So let's say the midpoint is t, and we have t minus tau here, and t plus tau here, and our signal changes slightly from between these 2 points. So our signal is sine or cosine omega t, okay? And exactly at the midpoint, we sample it and hold it here. So this is continuous time, so this is our time axis, this is our signal, and this is a slightly larger version of the same portion of our signal. We are assuming that our signal changes linearly from t minus tau to t plus tau. So we have these same points here. So this is, let's center our signal around t. So let's call this, minus tau, and let's call this tau. So let's remove t for the sake of simplicity. And let's say the change from these 2 points in time, from one point to another, is delta, one quantization step size. And this is our signal, x of t. So that is the worst case that is imaginable. Our signal goes from one value to another. And let's say this part is delta over 2. And the second part is also delta over 2. And we would like to zoom it even further to look at quantization error. So let's put minus tau and plus tau in here. And these points are delta over 2 and minus delta over 2. And this would be our quantization noise. So that's the difference between the quantized value, that is this value in here, and the signal itself. So EQ of t goes from minus delta over 2 to delta over 2. So then let's write EQ of t, assuming that it's linear, roughly linear. EQ of t is equal to delta over 2 tau, that's the slope of our line, times t. Then the mean squared error power, MSE power of our quantization error is defined as PQ. We average over 2 tau, and we get the integral of our error signal from minus tau to tau we're getting the integral of the square of our signal because we're calculating power. So delta over 2 tau squared t squared dt. So that's the power of our signal. So power of our error. That is equal to delta squared over 12. That's an important result. So I'm going to put a little star next to it. Okay. So we're going to come back to that star. So let us assume that the sinusoidal signal, or let's say a cosinusoidal signal, x of t, a cosine omega 0 t, it is varying between minus a and a. And we are using a b-bit representation. So the quantization noise power is then delta is equal to, so we need to use the quantization step size, that is 2a over 2 to the power b. We are using b bits, which means our quantization step size is 2a, that's the dynamic range, over 2 to the power b. We have so many numbers. And if you use this in whatever I showed you as a star in the previous slide, we end up with quantization error power as a squared over 3 times 2 to the power b. So this is quantization error power, which we're going to use in a moment. So how about the power of the sinusoid then? The power of the sinusoid, power of our signal, is px, which is equal to 1 over t. We're averaging over one period from 0 to t, a squared cosine squared omega t dt, which is equal to, you can calculate this in your own time if you like, which is equal to a squared over 2. So finally, we define the signal to quantization noise ratio, that is SQNR, which is given as 10 log 10 px over pq. So that is the signal power to quantization error power. That is equal to 10 log 10, 3 over 2, 2 to the power b, which is equal to 1.76 plus 6.02 b dB. So that means when you increase the number of bits you use for quantization by 1, you're going to have an increase in the signal to quantization noise ratio of 6 dB. So 1 bit means an improvement of 6 dBs. That means, say, if you are if you're quantizing your signal with 16 bits and instead you choose to quantize it using 4 bits, you're quantizing using